Hi everyone, I am Dr. Robin Khosla, Assistant Professor at School of Computing and Electrical Engineering, IIT Mandi. I'll be talking about my research project on development of CMOS compatible ferroelectric hafnium zirconium oxide and aluminum scandium nitride based semiconductor memory devices for non-volatile memory applications, which is sponsored by ANRF with this project number. So the outline of the presentation is for generic audience, the introduction, evolution of memory technologies, computer memory hierarchy, what are non-volatile ferroelectric memories, what is our approach on this project, and then the summary. Global semiconductor market sales has already exceeded 556 billion in 2021 and has already reached 1 trillion in 2026, which was expected to reach in 2030 initially, but because of the AI demand, it's already touched in 2026. In terms of energy consumption, nearly 415 terawatt hour of electricity is consumed by global data centers in 2024, which accounts to nearly 1 to 2% of the world's energy consumption. And this number is expected to reach nearly 1,000 terawatt hour before 2030, driven by the huge demand of AI. And this is equivalent to the combined electricity demand of an entire nation. So how the memory technology evolved over the years, if we see from 1947 onwards, with the introduction of random access memory, 1956, programmable read-only memory, 1961, static random access memory, 1968, dynamic random access memory, 1971, electrically programmable read-only memory, 1984, NOR flash, and 1989, NAND flash. So from 1989 onwards, the flash memory has dominated the market and is the technology what is used in solid-state drives as well as pen drives these days. So if we see the price per MB in US dollar per MB in 1950s, this has reduced from 10 power 9 to 10 power minus 4 in 2015 in SSDs or pen drives. In 2017, in fact, 3D expand memories which used phase change memory technology was introduced, but it discontinued in 2021. It turns out that it is very hard to beat the DRAM and NAND combo. Whereas in future, we are looking for new memory technologies like storage class memory. So let's see what is the computer memory hierarchy, how it looks like. It has CPU registers, which are having 14 transistors to store one bit very fast. As we move further down, we have static random access memory, which is actually cache memory, having 6 transistors to store one bit. Then dynamic random access memory, one transistor, one capacitor structure to store one bit. So these are all synchronous. As we move away, we have the solid state drives nowadays, which are having a moderate speed of the order of microseconds and a moderate cost. Further down, we have magnetic disks, which are cheaper, and then the archival tapes. As we move down in this hierarchy, the speed is reducing, area is reducing, and the cost is also reducing. So let's talk about non-volatile ferroelectric memories. First, how we classify the non-volatile memories. Non-volatile memories are based on charge-based, like floating gate flash or charge-trap flash. So the problem with them is that as we scale below 20 nanometer, or let's say sub 60 nanometer, the statistical fluctuation of electrons actually change the threshold voltage of such devices. So these are not reliable for scaling. Therefore, non-charge-based emerging memory technologies are being investigated, and still it's under research which one will actually win the race. So if you see the ferroelectric memory is one of them, then magnetic memory, phase change memory, and resistive memory. Among these, ferroelectric random access memory is actually very popular because it is non-volatile, it has fast access time, low power consumption, high security, excellent condition and endurance time, as well as it is radiation tolerant. Now, if we compare the ferroelectric memory with the technology in the market, it has a lower write time, lower read time, larger number of write cycles. Problem with this is basically the scaling as well as the material integration into the CMOS process. So let's see what are ferroelectric memories first. So ferroelectric devices achieve non-volatility by sensing and switching the polarization state of a ferroelectric capacitor. So this is the typical structure of a ferroelectric material. As you can see, when we apply the electric field, the center atom, for example, titanium, in case of PZT, will displace up and down based on the electric field. And therefore, it shows polarization. So we can measure it when we apply a positive electric field, the polarization increases. And as we remove the electric field, the polarization returns back to a remnant polarization state. Similarly, when we apply a negative electric field, then it goes to minus p sat or polarization state. And once we remove the electric field, the polarization return back to the negative remnant polarization state. So this way, these two states can be used to store logic 0 and logic 1 in a memory device. So typical device structure looks like this, where we have a one transistor and a one capacitor structure. Where in fact this is similar to a DRAM, but the dielectric is replaced by ferroelectric material. Another option is in the transistor structure we can replace the oxide with a ferroelectric material. So the problem sometimes comes is that the ferroelectric material react with the silicon and the interface is not good. Therefore, a buffer layer may be needed in between. So the emerging ferroelectric materials are like hafnium zirconium oxide and aluminum scandium nitride, which has been popular these days or from the past decade with the invention of ferroelectricity in them. Now the ferroelectric memory has been has attracted a lot of interest because these are CMOS compatible. So in terms of endurance, these show a higher endurance greater than 10.6 order. Both in data retention is also expected greater than 10 years. Switching speed is also very fast. And then the ferroelectricity is expected to be seen or has been demonstrated to below 20 nanometer thicknesses. Endurance means how many times the memory can be rewritten before wearing out. Data retention means how long the stored data will survive without power. Whereas switching speed implies how quickly a bit can be written. And the film thickness basically directly defines how small we can scale or how much we can reduce the area. So what is our approach? Let's talk about key challenges. What are there with the ferroelectric memory? CMOS compatible ferroelectric materials and devices. This is one issue regarding the integration. Then scaling challenge, how to reduce the ferroelectricity or get the ferroelectricity for sub 10 nanometer thicknesses. Then reliability challenges are there, retention, endurance, and backup issues. Our objectives are to develop CMOS standard sub 10 nanometer rather than film of HfZrO and AlScN, development of high switching endurance HfZrO and AlScN MFM capacitors, development of long data retention MFI structures of NVM devices. Summarizing, the proposed HfZrO based memory devices are CMOS compatible and could potentially reduce energy consumption in data centers, resulting in lower carbon footprint for consumer applications. While the proposed ALSCN based memory devices are targeted for stringent environments such as space and defense, where reliability is critical. Finally, I would like to acknowledge ANRF for supporting our research work.